So today we're going to be talking about conservation of momentum, and especially for when things do not stay in line with each other. So in our previous video and our previous examples, we've had objects collide with each other, but then stay in line with each other. They've either stuck together and kept going in a straight line, or they hit each other and their motion continued in a straight line. So this video covers what happens when they either weren't in a straight line to start with, or if they go off at angles like in the picture. So this is important. Conservation of momentum at angles is important for forensics. You can analyze car crashes. You can analyze spatter because of conservation of momentum. It's important for engineering. Rockets, again, we need to know how fast the jet fuel is leaving the rockets, or the rocket fuel is leaving the rockets, so that we can know how fast our rockets are accelerating. And we need to know how to make things that can survive drops. Do we want things that will cushion or break off on impact so that our main object won't be affected, or do we not want that? And then, of course, it's also very important for quantum mechanics and quantum physics and particle physics. A lot of what we know of some very detailed chemistry and very detailed particle physics is because of conservation of momentum. So, vectors are any quantity with magnitude and direction. We've said that a couple times, but in this video we are going to review vectors quite a bit before we get into our examples. So some other properties of vectors that are very important today are that they can be added in any order. That means if we have vector A and vector B, we can also add them B plus A. And we kind of know this in math and in algebra, because if we have 4 plus 2, that equals 6. But if we have 2 plus 4, that still equals 6. So the order of adding for vectors doesn't affect our result. They're also usually added head to tail, which means if we draw a vector, and in this case we have our vector going kind of up and to the right, the next vector we draw should start where that vector ends and continue onward. So we have head to tail. They can also be shifted around, so we can slide them horizontally and vertically with respect to its initial position, or the initial place that we draw our vector, so long as we don't rotate them. So these two arrows here, you notice they're parallel to each other. They are the same vector. If we just slide the vector over, it doesn't affect it. What affects the vector is its magnitude and direction. And we haven't changed the direction because we haven't changed the angle. So we can slide the vectors around and shift vectors around so long as we don't twist or rotate them. And vectors, a positive vector has the same length as a negative vector of the same kind, but it's going to point in the opposite direction. So if this arrow is positive B, a positive vector that we're just calling B, then this arrow over here will be negative B. Notice that they're parallel to each other and they have the same length, they're just pointed in opposite directions. And the last property of vector that we need to remember today is that they can be broken into component vectors. So if we have, again, our vector b, it has some component going up, and we usually call up the y direction, and it has some component vector going to the side, which we usually call x. And you can think of this kind of like either cutting through somebody's yard as you're walking, or being nice and walking along the sidewalk. They both get you to the same place, but one was horizontal and vertical and the other was straight across. Some other vectors that we've seen before are displacement, velocity, acceleration, force, and now we're talking about momentum. So all of these that we've seen are vectors. So these properties apply to all of those things. So for displacement, displacement is the change in position of an object, and some of the things that we did with displacement is, for example, if we have Sigmund RTA walk a kind of a crazy path where he goes northwest, southeast, and then northeast, we can find his total displacement first by finding the components. So each vector has a different color component, and then we can add those components in a way that we find easiest. So I'm going to add them first, the east and west components, and then the north and south components. So the first thing Sigmund did is he has a component of his motion that was west. And then the next component of his motion had a component that was towards the east. So head to tail, he's going to come back on the path that he started from, like so. And then the next east-west component continues east, so we continue from where we left the blue component, like so. And now we're out of east to west components, so then we can go up and down, north and south. So he went north, and then he went south, so the arrow comes back on itself, and then he went north again. And from start to finish, we call that the resultant. So remember, my yellow arrow started over here. So we go from start to finish, and I put that in green. So that is our resultant. And when we're talking about positions, that is also what we call displacement. So that is his total displacement. And if we compare that to our original diagram, we can see that this is the same. So it doesn't matter what order we add the vectors in, we will get the same result. For velocity, velocity is the rate of change in an object's position. One example for velocity that we often come across is when we have some sort of object crossing a river with a current in it. So in this case, we have Sigmund trying to paddle across a river, and the river has a current pushing Sigmund downstream. So Sigmund's resultant velocity is actually this white arrow, this white vector here. And the way we would calculate that white vector is a squared plus b squared equals c squared, which is the Pythagorean theorem. One of the legs, let's say the yellow one, we would make that a squared, or we would make that side a, this side would be b, and this side would be c, our hypotenuse. And then we could calculate that. And remember, how far he goes downstream does not depend on how far he goes diagonally, or how fast he's moving diagonally. It only depends on how fast he's moving downstream. And we would have a corresponding triangle for Sigmund's displacement. His distance or displacement across the river would correspond to his velocity as he paddles across the river. His displacement downstream would correspond to his velocity downstream, and his total displacement would correspond to his resultant velocity. This can also work if we're going in straight lines. What if Sigmund, now that he's on the other side, he is observing a boat that is also being pushed by the same current downstream? The boat observes itself to have some velocity, and that's the yellow vector, and the current still has the same velocity. So what does Sigmund observe the boat to have as its velocity? So we would add those velocities together of the boat's measured speed and the current's speed, and this would be the velocity that Sigmund observes, standing still on the bank of the river. We can also have acceleration, which is the rate of change in the object's velocity. And in acceleration, we had a lot of, we looked at one component in one direction. So while we had projectiles, say, we would look at the acceleration in the y direction because we were accelerating because of the force of gravity, but we would not have any acceleration in the x direction. So this helps us remember that the vertical and the horizontal components are going to be independent of each other. Finally, for force, which is a push or a pull on an object, we can have free body diagrams with all the vector forces pointing out of the object, like so. And then we can also have a vector addition diagram. Vector addition diagrams take advantage of the head to tail method of adding vectors, and they also take advantage of the fact that we can add vectors in any order. So what I did here is I took every vector from our free body diagram and I added it head to tail, and I started here, and I added it head to tail all the way around until there were no more vectors left. And because we end up exactly where we left, we know that there is zero net force acting on our object because there is no resultant force. The net force is another way to say the resultant force for an object. What if we have one force and make it a little smaller? So for example, what if we make the force that's going to the left smaller? Then our vector addition diagram will also get smaller. And now that there is a gap between our start and our finish for the forces, we have a net force that is not zero. So this object will accelerate. And remember, anytime we draw our vectors, we want to go from start to finish. So our resultant force is from start to finish. So the net force is going to be to the right for this object in this situation. So now that we have all that, we've reviewed all that, hopefully we remember all the different ways we can use forces. We add them head to tail, we can add them in any order, and we can move them around so long as we're not turning them. Now we can take a look at how we use those vectors in our momentum situations.